So let me just briefly summarize what we did yesterday to recap the main results. We introduced the electromagnetic field tensor, F mu nu, and we showed that it would transform under change to a new reference system like this. We made use of this fact to study how the electric and magnetic field in different coordinate systems would be perceived by an observer. And the two main equations that we arrived at were these. So these equations correspond to a situation where we have a reference system S prime moving with velocity v relative s. And so the field, the electric field and the magnetic field in this prime system are expressed via the electric and magnetic field in the unprimed system in the following way. And we also discussed a bit about how these equations actually imply that an observer here in S prime will experience a net field even if there is no net field in S, as long as there is a magnetic field. And we also mentioned how we can understand the phenomenon of spin-orbit coupling from these equations. Now, we started on a new topic yesterday, canonical transformations, and we'll continue with this today. So these are Hamilton's equations in the form we are used to seeing them. We have here the generalized coordinates and the canonical momenta. Now we know that we can always make a transformation on our coordinates to go, for instance, from Cartesian to polar coordinates. And that would be a point transformation where we introduce a new set of coordinates, large q, which are a function of the old coordinates, small q. But in general, in accordance with Hamilton's principle, we can make a transformation not only of the coordinates, but of the entire phase space. And by phase space, I mean the space spanned by the two n-axis small q and small p. So in general, we can write down transformation where we obtain a new set of coordinates, large q, which are a function of the old coordinates, but also, in general, of the old canonical momenta. And similarly for large p, we find a new set of canonical momenta that are a function of small q and small p. Now, there are infinitely many choices of such transformations, but this type of transformation is called canonical if the following is satisfied. If these transformations are in accordance with these two equations, relating the time derivative of q to the derivative of some function k with respect to pi. So basically these equations are equivalent to Hamilton's equations, but in the new coordinates. So k here is in fact a Hamiltonian in the new set of coordinates large q and large p. But there's a small twist which we have to be careful about. So to see what this is, let's first consider how we can use a modified Hamilton's principle to derive these equations. So basically what the plan here, just to outline the strategy, is that we'll first go through the mathematical details of how you do these canonical transformations and how they're related to the old set of transformations here. And then we'll have a look at a couple of examples to see why this is useful. Now recall that Lagrange's equations may be derived from the following equation. So this is the action of the system, and we're then demanding the variation of the action for the actual path taken by the system through this configuration space. Configuration space in the case of the Lagrangian, since we have q and q dot, should be 0. But we know how the Lagrangian is related to the Hamiltonian. So we can also write the following, which is known as the modified Hamilton's principle. So in order to proceed with this and see how we can derive Hamilton's equations from this requirement, let's introduce a function f. So we have something like this. which means that this is the requirement to be considered. Now, if you remember how we proceeded when we first derived these Euler-Lagrange equations from the variation of the action being zero, we obtained a few terms which were boundary terms after performing a partial integration. So we obtain these surface terms, or boundary terms, if you will, by considering the variation of each of the parameters that f depends on. Now, a property that we made use of was that the variation of the generalized coordinates at the end points of the trajectory should be zero. The end points should be fixed. And then we will consider every possible variation of the path between the two endpoints. So for this reason, the boundary term which looks like that is zero. But we now also get a different boundary term from the canonical momentum. Which looks up like this. Also after performing a partial integration. Now, there is no formal requirement of having the variation of the momenta at the endpoint being zero. So we cannot immediately discard this term, saying that this is zero. So what should we do with this term? So keep in mind here that all of these generalized coordinates and the canonical momenta are treated as independent variables. Well, we have two terms. So we just said that this term, we cannot in general demand to have zero variation at the endpoints. But there's one more term, this one. So if we consider f depends on q dot p and t, but there's no dependence on the time derivative of p. So we can replace the question mark here with 0. So both of these boundary or surface terms vanish. So by just going through the same steps as we did for the derivation of the Euler-Lagrange equations, we find these two decoupled equations. And we can evaluate what these equations are because we know f. So we just plug f into the equations. So the first equation should become this. Because df dq only gets the contribution from the Hamiltonian. There's no contribution from this term. And the first term only has contribution here. So that's the first. And the lower equation gives this. Because this first term here is 0. Since we have no dependence on p dot. So we have recovered Hamilton's equations. Now, to make a connection to this new set of coordinates, which we want to obtain via a canonical transformation, we've seen that these equations arise from the following requirement. Now, the canonical transformations regarding the new coordinates have exactly the same form as these equations. So it follows that this equation also has to be satisfied. So we're basically backtracking. We're starting with these equations for the new coordinates, and thus saying that the variation of this function here has to be 0. So by comparing this now, comparing the variation of the action as dictated by 1 with the variation of this action dictated by 2, we find that the following holds. Where now f is an arbitrary function, with one exception, it has to have zero variation at the endpoints. And the reason for why I've added this extra term here is that we see from these variational principles that you can always add a function, you can always add this as long as f has no variation at the endpoints, because we have df here. Now f is this twist that I mentioned to you. So f is very important because you can think of it, actually it's known as a generating function for the transformation that we're after. So let me explain to you what I mean. So f is known as a generating function, and in fact defines the transformation between the old and the new coordinates. So we'll see exactly how this works, but let me add one more statement to this. And that is that as long as f is a function of one of the old and one of the new variables, it's going to ensure that the transformation is precisely what we desire. It's canonical. So let's see how this works. Now, if f is supposed to contain one old and one new variable, there are 4 different combinations. Let's consider this one first. F is a function of small q and large q. Now we have the following general relation between the Hamiltonian expressed in the old coordinates, the Hamiltonian expressed in the new coordinates. So what we'll see here is that since we have this extra term allowed by the variational principle, this can be used to define how the transformation between the old and new coordinates must look like in order for this to be a canonical transformation. Now, since we know, or we have said here that f is supposed to be a function of small q and large q and time. So this means that we can write this total derivative by the product rule. So first we get the partial derivative of f. But then we have 2 extra terms due to its dependence on q and small q and large q. So now the question is, what kind of requirement or condition does this impose on f? In other words, for this equation here to be satisfied, what can we conclude about these partial derivatives of f? Well, we should be able to say this. So we have one term here that depends on q dot. And we have one term here. So these terms should be equal, which means that pi has to be the partial derivative of f1 with respect to qi, like this. Similarly, we have no dependence on q, large q dot on the left-hand side. And so we should have no dependence on large q dot on the right-hand side either, which means that these 2 terms have to cancel. And that gives us a requirement for how p must be related to this one. And we have one more inference we can make, and that is how the Hamiltonians are related. Because to have full equivalence, we see that h has to be equal to this. So we have this extra term here, which is the partial derivative of f with respect to t. So if f has an explicit time dependence, this has to be absorbed into the new Hamiltonian. Like this. So what have we obtained here? Well, we have obtained precisely the transformation equations that give us the bridge between going from the old coordinates to the new coordinates. So you can think of this as follows. Okay, small p is equal to this partial derivative. This partial derivative will in general be a function of small q and large q, since f is a function of small q and large q. But then we can use this equation here to eliminate the small q dependence, because we can plug it into here and then finally obtain small p as a function of large q and large p, right? And we can do the same thing here. And the virtue of these equations is that they guarantee that this transformation is canonical. So in this way, we say that f is the generating function which defines the transformation between the old and the new set of the variables and guarantees that it's canonical. So that was the first case. Let's consider also a second case. Namely that f is now a function depending on small q and large p, so one old and one new variable, and now this extra term here. Inserting now f into the general relation over there, we get this. So we get the time derivative of f2, but also the time derivative of this term, which is equal to these two terms. Well, that's convenient because we can then eliminate these two terms immediately, since they cancel. So by now expanding this total time derivative in terms of its partial time derivatives, I get this. So keep in mind that, as always, we consider these variables as independent. So we again just try to identify how the original coordinates and the new coordinates are related to the partial derivatives of f. So the following should do the trick in order to equate the left hand and the right hand side. So for a set of transformations that looks like this, f2 is the generating function. Now it's worth to note that there is an explicit connection between f1 and f2, which we have seen before. So what's the missing word here? f1 and f2 are related via something we made use of when going from the Lagrangian to the Hamilton formalism. Yep. They're related via this Legendre transformation, and we can see this because we've exchanged one of the coordinates in the two functions. So we have, for instance, this equation from f1, which I can integrate to obtain this. So when I integrate it, I get large Q, large P, but I also get an integrational constant in general, which looks like this. So it has no dependence on large Q, which means that it vanishes when I take the partial derivative. And this is precisely Legendre transformation. They're related. Their difference is given by the product of the two variables we interchange. Okay, I think we'll take a break there.